Hello, everyone. Welcome to my lecture again. Yeah, today we continue our studies for website designs. Yeah, in the previous lectures, we briefly introduced some important characteristic of transistors. Yeah, today we continue these studies. In today's lectures, we're gonna talk about more characteristics of CMOS, specifically the MOS capacitors, the threshold voltage, the leakage voltage of CMOS, and then the thermal effect of MOSFET. We also talk about some of the parameters used in the commercial software like SPICE, how this parameter incorporate into the simulations. Yeah. Then we may have some intellectual exercise at the end of today's lectures. Yeah. But the intellectual exercise will probably defer to the Thursday's lectures given by my students. Now let's first look at the transistor characteristics. So as we know that CMOS consists of the gate, yeah, which typically is made of polysilicons. Then there's a substrate in between. It's silicon dioxide, serving as the insulators. Yeah. So um, if we apply a voltage on the gate and the substrate, then the capacitor will be formed, where there's a charge accumulate on the gate, positive charge, and then a negative charge will accumulate in the substrate. Yeah, this negative charge essentially will form the channels. We talk about that. The channel will conduct current from source to drain. In between is silicon dioxide, which serves as insulators. Yeah, the thickness of this silicon dioxide is called XOX. Okay, so this is equation for the polycapacitors. They are actually a function of area, A here, and also it's inverse proportional to the distance of these two plates. Yeah, actually this is OX I just mentioned in previous slides. Here we have some of the coefficient. For example, the epsilon r is relative static permittivities, uh, which is sometimes called the dielectrics constant. Yeah, here relative related to the air. Of course, this is for the silicon dioxide. Then the epsilon zero is dielectric constants. Yeah, this is there's fixed numbers over there. This is the separation between the two plates. Yeah. So from this equation, you can see that bigger area will lead to big capacitors. Smaller distance between the plate will also lead to the large capacitors. Yeah. So essentially, we can reform this capacitance because this capacitance is pretty much formed by the silicon dioxide. So basically, we can write this unit capacitance as epsilon XO divided by the distance of this two plane, yeah, X or X, yeah. So basically, gate capacitance will help determine the charge in the channel, which form the inversion regions. So you have large capacitors, then large charge will form in the channel, and then they can conduct more current. So the size, the value of the capacitors essentially determine the capability of the MOS transistors in terms of how they conduct current. Okay, that's why it's very important. Another important concept related to the MOS capacitors, MOSFET, is that threshold voltage. Yeah, actually, I briefly mentioned the threshold voltage in the previous lectures. So today we're gonna have a little bit more detailed discussion of how the threshold voltage is formulated. Yeah, actually, if we really want to go to the deep of the threshold voltage, yeah, there's a very detailed discussion from the semiconductor books talk about lot of physical phenomena. Yeah, but in this class we just summarize the major conclusions. Yeah, which is useful for us to understand more materials in the later part of this lectures. So threshold voltage, as we know that is the voltage where we turn on the transistors. Essentially, turn on means that there's a channel formed underneath the gate. Because the gate and then the substrate have different, they are made of different materials. So as a result, when they put together, there's so-called flat band voltage. You need to overcome, for the electronic to pass that the channels. So this flat band voltage depends on difference in terms of working function between the gate and the substrate. Also depend on the fixed surface charge. Okay, there's formula for that. Then another second component for the threshold voltage is called the surface potential, which is number of the so-called bunk potential or the Fermi um, potential of the substrate. Yeah, substrate. Yeah, this actually is the characteristic of the um, substrate uh, properties. And then also because there's a depletion layer. Depletion layer means that the charge will be moving across the boundaries. And then, for example, if the positive charge moving across the boundary, then there's depletion of a positive charge in the one side, and then on the other hand, if the electron move to the other side, then there's a depletion of um, negative charge on the on this side. Yeah. So as a result, voltage will create because you have charge, and then you have this insulator in between. So or not insulation. Yeah. There's boundaries in between. So they will create this kind of voltage. Yeah. And then there's also ion implementation. Ion is kind of um, is the metal which have a positive or negative charge called ions. So we can implement some ion on the surface of this on the gate surface such that we can change the voltage of the threshold voltage. Yeah, this actually kind of additional manipulation in the manufacture process to make the threshold to some specific values we want. Yeah, so together this is the four major component for the threshold voltage. In addition to the four component we just discussed, the threshold voltage is also dependent on another fact, um, which is represented by delta VT. So this delta VT actually is a function of source substrate voltage indicated by Vs here. The delta VT is also function of so-called body effect gamma. Yeah, we will show the equation in the next slides. Yeah, so together, the substrate voltage is determined by the four component I just mentioned: the fly band voltage, the surface voltage, the depletion charge, and then the ion implementation, and plus this delta VTs. So together, yeah, this formula show that threshold voltage function of this four component we just discussed: the flyby voltage, the surface voltage, the depletion charge in the channels, and then the ion implementations. Yeah, those numbers are just one examples. Yeah, you can see the uh, the ion implementations, yeah, sometimes can significantly change the final value of threshold voltage. Yeah, that's the reason why, which is important because we can using this ion implementations to design specific threshold voltage we want. Also, here we talk about specific values for the body effect. Yeah, here gamma n for nMOS is zero point 0.1. So you can say the delta T actually is a function of the gammas, yeah, which sometimes is a constant. Then the substrate, the source and the substrate voltage, which count for the body effect. Yeah. So if you have a high SB, then you end up with a high delta V. Yeah. So in this way, we can change the threshold voltage dynamically. Uh, that means that we can change them even the device has been made during the operation of the device instead of during the manufacture process as we did for the iron implementations. Yeah, that's very important because we can dynamically change the threshold voltage such that we can later on change the performance of the circuit, for example, the leakage current dynamically. Yeah, that's one of the important optimizations we can do for uh, device operations. Now let's go back to the device parameters we talked about before. Yeah, K primes. Turns out that K prime actually equal to mu times COX. Mu actually is the mobility of carriers. COX is most capacitors we discussed. Yeah. So higher most capacitors than high K primes. Um, this K prime sometimes we call the process transconductors. With K prime, then the betas we discuss is equal to K prime times width length ratios of the device because we consider width length ratios. So this essentially we call the device transconductance. From this formula, we can see that if you have large capacitors, then you have large K primes and correspondingly large betas. That means that you have more powerful transistors to conduct current. Yeah. So this the uh, two parameters is very important to characterize how powerful this device can be. Now we continue review the this important equations. Yeah. So as we know that we have uh, different two regions for most transistors. Yeah, for the right hand side show this this curve. Actually, we discussed this one. Yeah, this show that how the gate to source voltage um, change gonna affect this the drain drain current because drain current essentially determine how power the transistor can driven next stage device. Yeah, it's bigger is better. Yeah, so at the same time, the gate to source voltage determine uh, what's the maximum current this ID can have. Yeah, can have. Yeah. So the this this equation basically it's very important for us to understand many of the designs later on in this class. Yeah. Here I just recap what we have learned in last lectures. Remember, we talked about three regions. Yeah, uh, we have linear regions, which is the top part of this these fingers. Yeah, basically show that in this linear region, yeah, basically the gate voltage is larger than both source and the drain. So as a result, we have a channel formed underneath the gate. Yeah, underneath the gate. Of course, you have this kind of shape because the drain voltage is a little bit higher than the source, but not high enough. Remember, they are still smaller than the VGS minus VT. Yeah, so the current will flow from the drain to source. Then if they are equal, right, this kind of like boundaries, yeah, VDS just equal to VGS minus VT. So as a result, gate and the drain essentially just different by threshold voltage. So the channel just form between them. Of course, close to the source part, and then the channel form is formed over theirs. Yeah, they can conduct current very easily. But still, overall, there is a current flow from the drain to source. But if we continue increase the drain voltage, then pinch off will happens. Yeah, so essentially, some portion of the channel is there's no channel anymore. But magically, there's still current flow because there's a very large voltage between source and the drain, because here you continue increase the voltage at the drain, right? So the voltage difference between the source and the drain increasing. So magically, they can still get the charge, moving from the source to drain. Yeah. Um, as a result, the current still can continue conduct, but the effect is that even you increase the voltage, the current does not increase too much. Yeah, but they indeed increase a little bit. Yeah, this is called a body modulation effect. Yeah, as one of the students pointed out earlier. Yeah, this sometimes yeah, it's related to so-called earlier voltage. Yeah. Okay. Another important sense I want to talk about for the transistors is that most transistor, um, even though they are turned off, but they still leak. Yeah, they still leak. Yeah, and then actually leakage right now become pretty significant as technology move to more advanced node. Yeah, so we cannot ignore the leakage, and sometimes leakage play the dominant roles. Yeah, in some of the designs. Yeah, I'm gonna talk about the so-called near threshold voltage designs. Yeah, so we need to understand what leakage come from. Yeah. Um, So substantial current actually is given by these formulas. Yeah, given by this formula. Yeah. So you can say they are function of the threshold voltage. They are function of this gate to source voltage, and they also are function of this kind of drain to source voltage. Yeah. Here's K is a Boltzmann um, uh, Boltzmann constant. T is the thermal temperatures. Yeah. S actually is called subthreshold slope. Slope. Yeah. Subthreshold. I'm gonna talk about this next slides. Yeah. Which characterize the weakening inversion current. Yeah. So so in general, as we can see from these formulas, if we have a smaller VT, right? Smaller VT, because here VT is in the exponential part of these formulas, also have a minus sign. So smaller VT with minus sign actually means that it's bigger. Okay, it's bigger. So as a result, smaller VT means that large leakage, large leakage. Yeah. This actually it's important because if we reduce the threshold voltage, then we end up with a large leakage. Yeah. Um, that's the major barriers for us to reduce the supply voltage. Yeah, I'm going to talk about this later. Then, so also, we can adjust voltage by changing the substrate BIOS, which is uh, the the one of the important way we can change this substrate voltage, as we mentioned before. So in this way, we can somehow control the leakage. Yeah. So here we talk about this as substrate. Uh, this as actually is called the slope factors. Yeah, yeah, which conceptually define the slope of how this leakage goes down. So the slope actually is 1 over s, 1 over s. So you can say if you have a smaller s, that means that you have a large 1 over s. That means that the leakage goes down much faster than if you have a large s. So um, so as a result, basically, we want to have a smaller s because we want to this slope goes down as fast as possible. Yeah, as fast as possible. Because that means that if you um, if you reduce threshold voltage, then the leakage current can goes down much fast. Yeah, much fast. Uh, but based on this formula, yeah, it's pretty much depend on this uh, device. Yeah, it actually is the concentration of these silicons, concentration of silicons. Yeah, typically S actually is a 60 millivolt per decade. Yeah, per decade. Yeah, because I is in the log scales. I is in the log scales. Yeah. Okay. So now let's talk about the how we're gonna design the VTs, yeah, in terms of real designs. Remember, we talked about that smaller VT, yeah. So you can see from the equation we show, right? Suppose we are in the saturation mode. if we are in the saturation mode, right, the theta will be 2, right? Remember? So if they are in the 2, right, smaller VT actually will lead to the bigger current because VT is minus VT, right? Smaller means that we end up with a large current, the drain current. Yeah, that's actually helpful for designs. But on the other hand, yeah, smaller VT indicate that the transistor will be more leaky because at the same of the look at the second graph, right? At the uh, same of the VGS, yeah. So you can say the this IDS, right, will be bigger with smaller VT, yeah. Because imagine, smaller VT means that we can easily turn on, turn off transistors. So as a result, even when we reduce voltage, the leakage will be large. Then we have a large VTs because that means that it's more difficult to turn on, turn off the device. So that, from that perspective, yeah, this is hurt because we end up with more leaky device, even though we have a large active current, yeah, active current. So we have these dilemmas, yeah, in the designs, because for a lot of low power designs, we want to reduce VT because we reduce supply voltage. Accordingly, we need to reduce threshold voltage to maintain so-called noise margin. Noise margin, yeah, but that hurt leakage current. Yeah, that hurt leakage current. Yeah, so we cannot, both satisfy the leakage current and then the performance of the device when it in the active regions. So I think starting 2010, right, there's a huge research going on in this digital design communities, try to push where design in so-called near threshold computing. Near threshold computing means that we kind of reduce the supply voltage to the very low voltage, such that the voltage even close to the threshold voltage regions. Yeah, look at here. Yeah, this point 5 is pretty much close to the threshold voltage. You can see. Then the supply voltage is kind of very close to these regions. Yeah, but we cannot further goes down. Based on the curve beliefs. Yeah, then you can say if we go that way, yeah, the voltage almost close to zeros. Yeah. There's a reason for that because if you look at right hand side curves, uh, let's look at energy, right? Energy, yeah. Actually, if we reduce supply voltage, then of course you reduce energy. That's good. But at some point, right, if you reduce voltage um, beyond this threshold, right, like here, threshold voltage, actually energy will increase. Yeah, energy increase. The reason actually is what? It's because the chip become more leaky. Yeah, become more leaky because accordingly you have reduced threshold voltage. Yeah, sometimes the leakage current can be even more significant than the active current. Yeah, so that's actually is the one of the drawback if you go beyond the threshold voltage. Another one is that actually the chip become much more slower because if you use less current, then it will make the chip slower because you have to take a longer time to discharge the 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 load of this device. Yeah, typically it's capacitance. Yeah, suppose device capacitance does not change, then you have to take a longer time to charge or discharge. Yeah, so you can see that the delay actually goes up a lot. Yeah, this actually even in log scales. Yeah, so in other words that you pretty much it doesn't really get anything after you reduce voltage beyond the threshold voltage, supply voltage. So people argue that probably the best trade-off will happen in this so-called near threshold regions. Yeah, still we keep the energy pretty low, and then delay is not significantly large. So the delay and energy product, delay performance product still win. So that's why this whole um, design strategy is called near threshold computing. Yeah, near threshold. I think this area is still active right now in these design communities. Yeah, but it's pretty much suited for extremely low power designs. For example, this design which medical embedded medical device which put out in our bodies, which can last for more than 10 years. Need very small energies, maybe powered by batteries, because you don't want to do the operation every 2 years. Yeah, something like that. Yeah, maybe every 10 years probably is doable. Anyway, so that's actually the applications. Yeah. Also, on top of this power leakage effect, then we also need to look at the thermal temperature effect. Yeah, uh, because temperature actually it's important parameters which affect the reliability of the device. Yeah, in other words, that if you hit temperature very high, then the device will age much fast, even fail much fast. Yeah. Also, in some situation, yeah, we could have so-called um, thermal runaway. Thermal runaway means that if you increase temperatures, then the leakage will increase. Leakage increasing will lead to the more high temperatures, and high temperature will lead to more leakage increase. So you end up with this positive feedback, and eventually the chip will shut down, totally break. Yeah. In general, the PN junction, CMOS PN junction can only sustain not more than 150-degree temperatures. Otherwise, the PN junction just break down. So if you look at all the Intel chips, pretty much they control the temperature around 100 degrees. More than that, the chip will be either temporarily shut down, or just they do some like throttling, frequency, reduce frequency, all kind of trick to reduce power of the chip. Yeah, so um, that's pretty much all this major the major chip companies doing right now. Um, so the temperature analysis of chip actually is a pretty active research area. As I mentioned in my previous slides, that today's chip actually, in some sense, is limited by temperatures. After the nail scaling is end, um, the temperature of chip is pretty much controlled by how many devices you're going to integrate. So the temperature control have to be very carefully designed to make sure the chip working on all kind of uh, condition and workload. Um, Actually, there's a whole bunch of research going on. I mean, model the circuit performance and then reliability, all these informations. Yeah, because you have to thoroughly verify those performance, reliability, timing, power before you send the chip to manufacturers. Yeah, I have one graduate level courses, E213 computer electronic simulation, which provide this analysis, mathematic foundation for this analysis. Yeah, so if you are interested in these courses, yeah, you can take these courses in the futures. Yeah, it's open to senior undergraduate student. Of course, majority is still graduate students. Yeah, so okay. Uh, this is just some of the parameters used by SPICE. Yeah, SPICE actually is most popular circuit simulators. Yeah, circuit simulator. Yeah, they use this kind of parameters. For example, this LW is length width, KP is K prime. This gamma is a body bias factors we just mentioned, and then this is a source strain area overhead. We compute this parathetics, and then this is zero CGSW is zero bias sidewalk capacitors, and the CGBO is zero bias gate over capacitors. Yeah, if you are really serious circuit designers, yeah, you have to understand all these parameters for each of the CMOS device. Yeah, so there's a whole bunch of informations, yeah, on the SPICE manuals. Yeah, here just give you one examples. Yeah. This is actually an lecture exercise. I suggest that the TA will give you this lecture exercise in the next lectures. Yeah, so here we just show these questions. Yeah, you can start to work on this these questions. Yeah. So if you are interested, you can work on these problems. Yeah, and then the team will have discussions on answers in the Thursday lectures. Okay. Thank you.